plan here is to work through a sample problem that you will need to do for Lab 36. And so I've made up some data, and the data will be, in case it's not readable on the film, is that we'll have the mass of the metal is 25.00 grams. The mass of the water is 50.00 grams. The initial temperature of the metal is 98.4 degrees Celsius. The initial temperature of the water in the calorimeter is 25.0 degrees Celsius. And after the two are allowed to mix, the final temperature of the mixture will be 28.4 degrees Celsius. The next thing we'll do is we'll talk a little bit about the theory. The theory is that the heat lost by any process has to be numerically equal to the heat gained by the other material. And so what you see there is you will see that we have heat lost, Q lost, is equal to Q gained. Apologies on the filming. So the negative of the Q lost is equal to the Q gained. In this experiment, the metal is losing the heat and the water is gaining the heat. So the negative of the Q metal equals the heat gained by the water. Now, since we know that heat equals the mass times the specific heat times the change in temperature, we will substitute that in on both sides. Then what we will do is plug the numbers in. The mass of the metal was 25 grams. What we're trying to find in the problem is the heat capacity of the metal. And the change in temperature, since that's always final minus initial, is 28.4 minus 98.4. When we plug the same numbers in, or numbers for water in, we will get that the mass of the water is 50 grams. The specific heat capacity of water is 4.18 joules per gram degree Celsius, and the change in temperature of the water will be 28.4 minus 25 degrees Celsius. All we should have to do now is solve the equation for C sub P. I'm going to do a little adjustment here on the camera. Hopefully you can still see everything. So now it's just a matter of grinding out the math. And so we'll do that. The calculator. Negative 25.00 grams times C sub P times negative 70.0 degrees C will be equal to 50 grams times 4.18 joules over gram degree Celsius times, and that difference, 28.4 minus 25, is 3.4 degrees Celsius. The grams and the degrees Celsius on the right side of the equation divide out. What I'm going to do now is just do the multiplication. Keep in mind that when I multiply a negative 70 by a positive 25, I'll get a negative answer. But since I'm taking the negative of all of that, The two negatives essentially cancel out or divide out. So 25 times 70 is 1750, and the units are grams times degrees Celsius times C sub P, which is what in math you would probably say is X. If I multiply 50 by 4.18 by 3.4, I get 710.6 joules. Algebra says divide both sides by 1750 gram degrees Celsius. The degrees Celsius, the grams, and the 1750 divide out on the left. So I get the specific heat capacity of the metal to be 710.6 divided by 1750, which, when we do the math, our answer will come out to be 0.406 joules over grams degrees Celsius. What you may be able to see on the board is the formula for percent error. Percent error in chemistry is calculated by taking the absolute value of the difference, so subtract, the true value, which is the value that's in the textbook, and subtract from that the measured value, which is the answer that you would have calculated. Get that difference, divide it by the true value, and multiply it by 100. In our example, we calculated the specific heat of the lead to be 0.406 joules per gram degrees Celsius. So that would be the measured value. When I look up the value in the book, it's 0.159 joules per gram degrees Celsius. So if I were to start plugging the numbers in and solving the equation, I get 0.159 minus 0.406, and so that difference is a negative 247, but I take the absolute value, so 0.247 divided by 0.159, and I get 1.55, which I then multiply by 100, which is 155% error, which is not very good, but that is those are the numbers, and that's how it works.